Hello. Today we're speedrunning AP Chemistry. I was an IB student. I've graduated now. I did physics, and I haven't done any chemistry since grade 9. I don't remember any chemistry. I barely know what chemistry is. It's like potions and you mix stuff, right? Physics is the ultimate, most fundamental science after math, but I will learn chemistry anyways out of respect for chemistry stuffs. Cool. Let's get started. Okay, so if we take a look at my Speedrun Learns Notion notebook, we've done special relativity check. Now we're doing AP Chem. We're going to use Khan Academy, the entire AP course on Khan Academy. Apparently acids and bases is short but deadly according to my friends. And it's a total of 6,600 mastery points, average of 800 to 600 per section. So that's a lot. The strategy is to do the quizzes first, and then that means I take in the information better when I go and get everything wrong and need to watch the videos and read the articles to learn how to get it right. It means it's like being told you're wrong. So you listen because you are actually wrong. Yes. Okay. First up, we've got atomic structure and properties. That should be pretty easy. That's just like atoms and electron orbits something, right? So we start with the quiz. Yeah, sure, I'm ready to practice. Straight into it. Using the information in the table, calculate the number of formula units in a 62.2 gram sample. Aluminium sulfide. I'm dying already. What? Yes, that's what my question is. What is a formula unit? Fundamental unit of an ionic compound. Calculate the number of formula units in a sample of an ionic compound in the same way that we calculate the number of atoms. Okay. Okay. And the number of let's watch a related article. Wait, so what do we have? We have the molar mass. Oh, is the formula units how many moles it is? Okay. So if we have 26.98 grams per mole, get out my papers. Okay, swap. We put that like there. Let's get this set up. Uh, 26.98 grams in a mole, and we've got 2 of them, so that's 2 moles. What? No. Frick, this is physics and I can't even do that. What? It's a 62.2 2-gram sample. I give up. Well, no, I don't even know. No, I want to use a hint. Grams to moles of this substance. Use the molar mass. What are we looking for though? I know what Avogadro's number is. Worked example. Calculating molar mass and number of moles. What are we looking for? Formula units? Is there like a guide on? Okay, let's watch this worked example. Okay. Okay, start recording. Here we go. You're about to die. I'm pretty sure formula units is moles. So if we have 26.98 grams per mole, let's find out how many moles that is. We got 26.98 grams per mole times how many aluminiums do we have? 2. And we've got 32.06 grams per mole times 3 of them of silicon. And that gives us a big number. Where's the calculator? Oh, you might need a calculator, really. Okay, calculator. What? Three, 2, 6 times 150.14 grams per mole of this thing, aluminium sulfide. And we want how many moles it is, so we multiply it by Avogadro's constant. No, we don't. How many grams do we have? Oh, we have 62.2. Okay, so if it's 150 grams per mole, and we have 62.2 grams of it, 150 divided? No, 62.2 divided by the 150.14, because it's like what fraction of a mole do we have? If 150 is the entire thing, we have 62 of that. That'll give us how many moles we have. Oh yeah, and you can cancel the units as well. That's big number. Why is chemistry gross? I never said that. A smaller calculator. There we go. Okay, 62.2 divided by 150.14. Significant figures. Lowest is 1, so I guess we go down to 1. 0.4. Not quite. Wait, what? Is it not moles? What are formula units? The lowest whole number. The what? Empirical formula. It's the lowest possible ratio of the cations and anions of a given ionic compound. Table salt has a formula unit of N sodium chloride. Sodium chloride ions are in a 1-to-1 ratio. Ammonium nitrite has a formula unit showing the ions in a 1-to-1 ratio. So it's the ratio of the ions? What? But that's not what this says, does it? Oh, we need to go from moles to representative particles. Yeah, we got the molar mass. We got the number of moles, and which I didn't write down. Where are we? Okay, yeah. Finally, let's use Avogadro's number to convert from moles to formula units. Wait. Avogadro's number is 1 over... Wait, what was Avogadro's number again? Was it grams per mole? Or was it per mole? Forgotten everything. Number of, it's the, number of molecules in 1 mole. So it's molecules per mole. So we're finding number of molecules. Wait. So 0.414 divided by 6 point, what was it, 3? 6.022 times 10 to the 23. Sorry, multiplied by, what am I doing? Yeah. I also wrote 10 to the 24, and I said 23. Brain. What? Yeah, okay, give up time. Slap the calculator. We're using the calculator. I suck at this. Come on. .4. I don't know how to use this. 10 to the power 23. 2.4 times, I don't freaking know how many zeros there are. Is that right? Times 23? Okay, so I do know how to use the calculator. So we got 1, 2, 3 significant figures. So, I mean, I'm basically just looking at the answer, but I did get the right answer. 10 to the power of 3 times 1, 2, 3, 4, 5, 6, 7, 8, which is 24. What? That's what it says. 23. Calculator has started. Or not. Okay, whatever. Yeah, okay, it is 10 to the 23. I just can't use the computer calculator. So formula units are literally just the number of molecules in the substance, which you can get from the number of moles using Avogadro's constant, which is the number of molecules per mole. So you multiply them and you get the number of molecules. Cool. Calculate the number of atoms. Molar mass is 69.72 grams per mole, which means we have 27.2 divided by 69.72 moles. And we want the number of atoms, so multiply by 6.022 times 10 to the 23 Avogadro's constant, and we get 2.35 times 10 to the 23. That's the number of atoms. Wait. The difference between atoms and what did I do wrong? Milligrams. Okay. So that's that thing. Milligrams is times 10 to the negative 3. So I times 10 to the negative 3. So I subtract 3 zeros from the end of this thing. I want to die. I basically got that right. Okay, using the information in the table, calculate the number of moles. Kilograms, sample of aspirin. That's aspirin? Chemistry's kind of cool. Okay, all we need is the number of moles, so 1.008 grams per mole times how many grams? Sorry, no, how many hydrogens? 8. Hydrogen, 8. H. carbon, we have 12 grams per mole times 8 of these plus 16 grams per mole. Wait, did I do that right? Yeah. Of times 4 oxygens, 168 grams per mole of aspirin. And we have 7.89, which is 7,890 grams of it. So we go 7,890 grams divided by 168 of them makes 1 mole. So we see how many of 168 of them fit in. And it's 46.9 of them. But we're going to 4 significant figures, so 46.92. No, we're going to 3, never mind. 46.9. Are you kidding me? Why is this wrong? I calculated the number of total grams per mole. Hydrogen times 8, 12 times 9. I multiplied it by 8. Are you kidding me? Now we have 43.8. Wow. So happy. The molar mass of sulfur is 32.06 grams per mole. Calculate the mass in grams of a sample of S containing sulfur containing yes. The mass, if it has that many atoms per mole is Avogadro's constant. So we multiply that by Avogadro's constant, 0.1. 6.022 times 10 to the 23 is Avogadro's constant. And then we get the number of moles. But we now have the number of grams per mole. So we multiply these two together to cancel out the moles. So it's like you have this many grams per mole and we know how many moles we have. Then we multiply them to find how many grams we have. 3.88, yes, times 10 to the 49. I'm not gonna bother checking. 88, yes. 49, right? How? That was so simple. I swear we did it right. Atoms per mole times the number of moles gives me that amount of moles. And I take that amount of moles That's 32.06 times that amount of moles. We have 1.2 times 10 to the 48 moles. What if, oh, maybe it's like a significant figures thing. Times 10 to the 48 moles times 32.06. No, that's basically just 3.88 times 10 to the 49. Why am I wrong? Please tell me. $107. Okay, that's totally different. Wait, they divided it? Yeah, that makes sense. You don't multiply it by the atoms per mole, you multiply it by the moles per atom, because you have this many atoms and you want to go per every atom. Why do I do this? Yes, okay, fine. So you just multiply it by 1 over Avogadro's constant. Yay. Okay, and then you use this thing. And then you've got the number of moles times number of grams per mole, because that's correct. Oops. You get 107. Show summary, we got 0 out of 4 correct. Let's go. Well, we did all of them. Next, mass spectrometry of elements. Ew, gross graph. Okay, chemical elements that do not exist in nature but that can be created in a laboratory are known as synthetic elements. Moscovium is a synthetic element with atomic number 115, was first synthesized in 2003. A hypothetical mass spectrum for a sample of moscovium containing 10 atoms is shown below. Thank you. So it looks like we have 3 atoms with an atomic mass of 288.2, which makes sense. What is a spectrum? Is it like the atomic mass spectrum? Oh yeah, okay, I just read that, I'm dumb. Information in the spectrum, calculate the average atomic mass of... Do I just multiply number of atoms by by their masses and an average? Let's see if that works. So we have 3 288.2s plus 289.2 atoms that have a five of those plus 290.2. Shut up, 290.2, and we have 2 290.2s. And we divide that by 10 because we have 10 atoms. And we get 299.1, 4 significant figures, okay. I'm a god. Not really. I didn't mean that. mass spectrum for an average sample of a pure element is shown below. Which of the following is the identity of the element? I don't know. What's the identity of an element? What is an identity? Oh, okay, which element is it? I didn't look at the answers. I don't freaking know. How am I supposed to know that? Do we get a periodic? Yeah, we get a periodic table. Wait, so I find the average mass. I'm just gonna try this. I'm gonna find the, wait, relative abundance. So it's 20%. Is it just which element is the most abundant? Okay, so 74, atomic mass of 74. W for the win. It's not even there. Wait, which is the... No, that's the proton number. The bottom is, so 74. Ass. Or get. Is it get or is it ass? Both of them are there. I don't know. Okay, well, 74 is the most, but it kind of ranges around. Wait, so we got ga, get, ass, and in. Ga, get, ass. Or is it in? Is it indium? Where is indium? It's not even there. Okay, so we got ga, get, and ass. And ga is 69.72. Get is 72. Ass is 74. Where do we average? Let's go. We average around this 73. So it's get. I'm sure I'm supposed to like actually calculate the average using the percentage. But meh. The mass spectrum for an average sample is shown below. Based on the spectrum, which of the following is true about the element? The element has an average atomic mass. The most abundant isotope of the... What's an isotope again? It's like when it has more electrons or something. What's an ion? I should know this because I did know it. I forgot. It's just words as long as you know what it means. Most abundant isotope of the element has an atomic mass of 64 units. An average sample, less than 20%, have an atomic mass of 66. Can I select multiple? Okay, well... Atomic mass of 66. Less than 20%? No, that's wrong. Element has an average atomic mass of 64. Don't know about that one. It'd be higher than 64, right? Like 66 maybe. Is that the top one? The most abundant isotope of the element has an atomic mass. I don't think that's true. Thank you for telling me I'm incorrect. The element has an average between 66 and 68. 4 peaks, yes. Each corresponding to a different isotope. The isotope with a mass of 64 is the most abundant, followed by 66. Together, these two isotopes make up more than 80% of the sample of the world. This suggests that the average is between 64 and 66, not 66 and 68. Okay. Why would the most abundant isotope of the element have an atomic mass of 64? The tallest peak corresponds to the most abundant isotope. In this spectrum, the tallest peak is the one at 64. What is an isotope? Isotope. Isotopes. Isotope. Isolated tope. I don't know. They have different amounts of neutrons, whereas an ion has extra electrons. I should remember that because I just closed my browser. Ah, man. Oh, we might be okay. Did we get kicked? No, we're still there. Okay, cool. Because you get ion propulsion, which is electricity going zap zap with the air, but you're throwing ions out, so the momentum takes you forward. The difference in momentum. Average atomic mass of silver, 107.87. Which of the following mass spectra could correspond to an average sample of silver? Well, the average mass is 107.87. A, a little higher than 107. This average is like 108. Do I need to actually calculate this? 107.87. Well, it's not these two. So it's A or C. C's average is 108. So it's not that. What? Surely it's A. Why? Yeah, I knew that. Wait, what did I just do? Oh, I did a dum-dum. D. Oh yeah, because it could be close. That's what I was doing. Yeah, this one kind of looks close to 108, and we're looking at a high 107. This one has way more than 108, so it's probably this one. It still says up next for me is the first one. That's cool, thank you. Oh, I'm not recording. Okay, I'm gonna take a break and I'll be back. Just like a 2-minute chill. Whew. Okay, timeout. I scored 100% on that quiz for like the first half of the first section out of like 8 sections, and that took me 5 hours. No, 3 hours. Because I started at 2 o'clock. That took me 3 hours to do one section. And I realized that sections repeat. So how it works is you get the points for doing all these practice things, but that's 4 questions for every single practice thing. So if I just take the quiz at the end for the straight 800 points straight up, I could just clear a section quicker. And then I could go back and then be more optimized by only working on the thing that I got wrong, right? So from now on, we're just doing the quiz at the end. What I'll do is I'll record this so you can watch me doing my working, and I'll flip the video so that you can see it the right way, right side up. Maybe not. I like having a face cam. I feel like that's more interesting. So like that angle. I'm actually so lazy, but I'm gonna eat dinner now at 5 o'clock so I can just like not have to worry about that. I was also hungry, so I'll see you in a bit. All right. We are beginning our second session. I've eaten dinner and I'm feeling rejuvenated. Right, we're back and we're doing the second quiz, skipping everything, going straight to the second quiz and hoping for the best, but we're gonna backtrack. Okay, photoelectron spectra of the 2p electrons of O and oxygen and chlorine are shown below. Okay. Which of the following best explains the difference in signal intensity for the 2 peaks? Photoelectron spectra of the 2 proton electrons. Is that what it means? No. Well, they wouldn't have 2 protons. What? 2p. Yes. Okay, so we need to know what photoelectron spectra is. Binding energy. Yeah, okay. Intensity. So what's this trying to say? We've got intensity, binding energy correlating with against intensity. Which of the following difference in signal intensity for the 2 peaks? What is signal intensity? Oh, okay. Well, intensity is the vertical axis, so chlorine has more intensity than oxygen. So what does that mean? Oxygen has fewer valence electrons than chlorine has, fewer protons than chlorine has, but chlorine could have more electron subshells than oxygen. Chlorine has more electrons in its 2 proton? Wait, chlorine is not 2. What is P? I don't know what P is. Subshell. Is that like the orbit? Then oxygen. Oh man. Can we watch videos? Yes, we can. Epic, epic, epic. Yeah, what are subshells? Yes. Oh, here we go. SPDF. Subshells are designated by SPD and F. S P What is this? S, P, D, and F, and each letter indicates a different shape. Spherical orbit. S is spherical, P is dumbbell, at right angles to each other. Most of organic chemistry of carbon-containing compounds, central to biology, involves interactions between electrons in S and P subshells. Yeah, okay. So they're the most important subshell types to be familiar with. However, atoms with many electrons may place some of their electrons in D and F subshells. Subshells D and F have more complex shapes and contain 5 and 7. So they're only showing P and S. Cool. This is not helping. Signal intensity. Valence electrons. Yes, I know what those are. They're the outside electrons and they get transferred, and that's how static electricity goes boom boom. Right? Periodic trends and Coulomb's law. Let's watch that. I'm hearing energy. Oh, here we go. Spectroscopy. Okay, experimental technique used to determine relative energies. Yes, photoelectron spectrometers work by ionizing samples and then measuring the kinetic energy. Okay, so you can get something from that. Okay, and then you use this formula. A PES spectrum is a graph of photoelectron count versus binding energy. Photoelectric effect was characterized by my guy Einstein. 1905. Nice. Photoelectric effect. Electrons are exposed in a metal are exposed to light of sufficient radiation. The electrons are then ejected from the metal surface. That's interesting. Yes, very interesting. Cool. Okay. Data obtained as plots of photoelectron count versus binding energy. Okay, that's not intensity though, right? Count. Right, intensity. What was intensity? I forgot what intensity was. There is a proper definition of intensity. Anyways, let's see if it comes up. Okay, relative number of electrons.
You've been gone for so long.
really understand these P and S things. Where are they squared? P is spectrum of neutral calcium. How do you know the electron configuration for calcium? So we have 5 peaks, 5 subshells that are closest to the nucleus. The peak with the highest binding energy, which is yeet this way, corresponds to the 1s subshell, while the peak with the lowest must correspond to the 3p subshell. Electrons in the 5 subshells closest to the nucleus: 1s, 2s, 2p, 3s, and 3p. So we only have one element in its 3p subshell. 3p is half the height, which suggests that there is only one electron in the 3p subshell of our mystery element. Of the 1s, 2s, and 3s, okay, kind of helps. Valence electrons. Thank you. Groups. Oh yeah, group theory is used quite a bit in chemistry, right? Does he talk about the P's and S's and stuff? Doesn't look like it. I want to know about the S's. Dem P's and dem S's. Shells, subshells, and orbitals, okay. Okay.
Mind into this body's young brain, it did what young brains do. It shoved the bad thoughts into the bag and put a wall around them.
This is new stuff. Okay. I get that. Okay, bro. Yes. Okay, I get that now. Intensity is like power per area. So oxygen is 8, chlorine is 17. Chlorine has more electrons in its 2p subshell than oxygen has. Two p is the second subshell of the second most orbit. What is the difference in signal? I see. Okay, I get that. The binding energy of the electrons closest to the nucleus is the highest. So it makes sense I would go lower on the way out. Yes. Okay, and then now why are we talking about the difference in signal intensity? We're talking about where the 2p electrons are. S was the first one because it's S for spherical, right? So you've got two S orbitals, then you got 4p orbitals and 6 and something. Yeah, here we go.
You've been gone so long.
It's 1? Wait, no, it's not 1. There's 2 orbitals in the first thing.
You're beautiful. Oh, you're so big. Last time I saw you, you were 6.8 centimeters. Now, look at you.
Wait, no, there's...
I'm sorry.
Yeah, there's 2 orbitals in the S orbital. There's 2 things, whatever. Okay, cool. Okay, what best explains the difference in signal intensity? That would explain it. Because then there's less energy binding, like there's less positive charge for each electron. Chlorine has more electron subshells than oxygen. No. Chlorine has more electrons in its 2p subshell than oxygen. But that's not why the signal is different. Like you could have heaps of electrons, but if your positive charge is the same, maybe even the electrons would repel each other, so. Oh my days. It affects binding energy, not signal intensity. Signal intensity is affected by having more electrons. Fuck. My god. Oh, frick. Next. First four ionization energies for elements X and Z are shown below. Kilojoules per mole. Okay, ionization energy. Kilojoules per mole. 900 kilojoules per mole to ionize? Okay. What's going on? Cool. Okay. Element X and element Z. which correctly identifies them. How am I supposed to tell how much ionization energy is required? Well, one requires a lot more. X requires a lot more than Z.
It did what young brains do. It shoved the bad thoughts into the bag and put a wall around them.
Okay. I can read, yes. Wait. So the valence electrons are the column number in the periodic table. Wait. Well, it looks like we have 2 valence electrons. This also has 2 valence electrons. So, okay, they're both in this line of stuff. So B, E, M, G, C, A, S, R, B, A. Oh, okay, and we just figure out which is bigger. Don't need to do any calculations to actually figure out which is which. Okay, so one requires more energy than the other. X requires more energy. Would that mean it has more protons? Higher positive charge? I'm gonna go with that. So Mg would be X. Beryllium would be Z. What? Didn't explain why they decrease. Apparently they decrease as you go down. Why would you decrease the more protons you have? Doesn't that mean you have a higher charge, so it's harder to remove it? So magnesium should be harder to remove, right? Okay, why does the apple logo have a bite? Why do first ionization energies decrease down a group? Oh, that's the group trend. Oh, these are called groups. Okay. So groups, periods. Okay, cool. I don't want to spend too much time on this. first. Oh, it's not the first as in the closest to the nucleus. It's the first as in it's the first that you take off the outermost shell. Of course, it's like the more shells you have, the more electrons you have repelling each other, so it's easier to take off the... Okay, so first should be higher for an element that's up, which is beryllium, which is that. Okay, yes, I get it now. Okay. Which of the following is the most likely empirical formula? Of the ionic compound that forms between gallium and oxygen. What is an ionic compound, man? Actually, I do remember, I think, what ionic compounds are. You can attach atoms by removing valence electrons, creating ions, so that they attract each other better, whereas when they were still neutral atoms without the ions, they would repel. I think that's it. Okay. But wait, how did he figure out how many, like what the charge is gonna be? How did he figure that out? Here. What? A halide? Okay, so I'm supposed to just know that halides gain an electron? Oh, it's a halogen. Okay, that makes sense. Wait, how do I tell? Okay, there's got to be a video on this. How I tell how many electrons I gain or lose. That makes sense.
Grandpa, I think
Yeah.
you put your mind into this body's young brain. It did what young brains do. It shoved the bad thoughts into the bag and put a wall around them.
Okay, so they want to gain one. So the group is number of valence electrons. What about 8? Okay. This is cool. Wait. 2 means it has 2 valence electrons. What does 18 mean? Okay, yeah, you can have 18 valence electrons. Yeah, so we want the ionic compound between gallium and oxygen. Oxygen on the periodic table is here, so it wants to gain 2 electrons to get a full outer shell. So it goes 1 electron, 2 electron, and then these are all full shells. Gallium, where's gallium? Right, gallium's here. So gallium and oxygen. Gallium has 13 valence electrons. Oxygen has 16 valence electrons. So it wants to gain 2. Gallium wants to gain 1, 2, 3, 4, 5. But it's easier just to lose 3 than gain 5. So it loses 3. So plus 3. And oxygen is a charge of -1, 2. So plus 3 and 2. So C, because if you have a plus 3 and a -2 charge, in order to make them equal, you multiply the -2 by 3 to get -6, the plus 3 by 2 to get +6. They cancel each other out, so they connect with 0 charge. Okay, that is a good, like, I don't know, 100 points or something. Ground state electron configuration for an element contains an unpaired 3s electron. The what now? The ground state electron configuration. What's an unpaired electron? Oh, so 3s. Wait, S is... how can you have 3? Wait, your electron orbitals are like S. So you got S1 and S2. And you got P. P1, P2, and like P3 or something. So 3s, which means you've got 3 in your first shell. So isn't that just the third element? So lithium? Wait. What is an unpaired electron?
Am I dreaming? Who are you?
My name's Finn. Are you my...
It is you. Oh my gosh, I can't believe you're alive. My nerve above. That's my son.
Okay. What is a ground state electron configuration? Is that just when it's neutral? Well, I assume ground state electron configuration. Male or gender. Not an ion. Wait, so an ion can be in ground state as well. Wait, are you knocking?
Shall we play pool?
Ah, yeah, sure.
Okay.
Alright, I will come back to this. Well, we are back with a main caveat. Obviously, I'm gonna do this in 2 parts, and I'm gonna try to finish all of it tomorrow. Today was just figuring out what's the fastest way to get through this. Is it recording the right screen? I sincerely hope so. Okay, so quiz 2, we're gonna resume that. The ground state electron configuration for an element contains an unpaired 3s electron. So, okay, is the internet gone or something? What is happening? Microsoft Edge is not responding. This is great. So there was a bit of an unfortunate glitch with Microsoft Edge, and it's deleted all my progress. I don't want to do quiz 2 again, so I will see you tomorrow, waking up at 5 o'clock to do chemistry. See ya.